Awesome. Thank you all so much for having me today. And before I begin, I want to quickly thank my collaborators and my sponsors for making this research possible. So throughout my career, I've made it a mission of mine to collect as many engineering degrees and backgrounds as possible, including electrical engineering, mechanical engineering, bioengineering, and most recently, computer science and engineering. Anybody else collecting degrees around here? Okay, a couple. Awesome. And so my research on making biosignal interfaces accessible is a culmination of all those backgrounds, and I'm really excited to share that with you today. So first, I want you to take a second to think about what kinds of machines and devices that you've operated today. Maybe you use a smartphone, maybe you drove to work, maybe you are on your laptop right now. And as you use these machines, what kind of assumptions are these machines making about your abilities? Maybe your car is assuming that you're at a certain height and weight as a driver. Maybe your smartphone is assuming that you have the strength to hold a smartphone and the dexterity to finally navigate all those tiny little buttons. And in particular, your machines and devices are making assumptions about our abilities and developing models so that they can interpret our intended interactions from sensors like the capacitive panel on the touch screen, a load sensor on a gas pedal, or mouse movement. But who fits into these assumed abilities, and how can we better design such interfaces such that the diverse abilities we see in this world are integrated into the development of these algorithms and sensors? So at this point, you might be thinking, well, why not just design for the average so most people can use these technologies? So I'll give you an example from Aviation that really highlights the importance of ability-based design and personalization. So as Sarah Hendren recounts, in the 1940s, the US Air Force was experiencing a high incidence of crashes during flight training. And when a scientist was commissioned to identify the cause of the crashes, they noted that all the cockpit structures had been built to the specifications for an average military recruit. But when they went ahead and measured these soldiers, none of the soldiers fit the 10 dimensions that had been considered when building the quote-unquote average cockpit. And so the conclusion that the scientists came to was there was no such thing as an average pilot. The unyielding fixity of the average cockpit ended up being useful to exactly no one. Right, and from there, the engineers began to make all these changes to the cockpits and made it be able to be personalized to each person's body types, and safety and comfort for the pilots significantly improved. And so similarly to how the aviation engineers personalized the cockpit in the 1940s, I'm interested in understanding how we can build individualized adaptable interfaces to customize human-machine interactions for people with and without limited movement. And my area of research that I'm really excited about is an area of research of developing next-generation brain/body-machine interfaces that could be used for accessibility and help, and improving that for people with and without disabilities. And there's several reasons why I'm really excited about this next-generation technology. First, biosignals by their nature fluctuate from person to person and from day to day and may require individualized interfaces, which is really awesome for personalization and ability-based design. Additionally, biosignals tend to be a little bit higher up the neural circuitry, so even if somebody has a stroke and can't use a mouse, they might still be able to use sensors placed on the person's muscles or their brains and be able to control a mouse still, or be able to control a cursor. Lastly, always-on sensors, or sensors that are always on the body and continually monitoring the person, could be really useful for continuous health monitoring. And in my research, I primarily focus on a type of sensor called electromyography sensors, which uses sensors on the person's muscles to sense muscle electrical activity. So today, I'll tell you about two different ways in which I enabled individualized adaptive interfaces using electromyography input. And the first way we did this was by doing real-time adaptation using a linear regression model. And the other way that we did this is by developing individualized gestures for each individual using K-nearest neighbors model. And you might notice that both of these models are very simple and kind of the most basic models that you can have. And that's because we are customizing the algorithm to each particular person. So we have very, very small data sets. And it actually works surprisingly well, as I'll show you in my talk. So first, I'll talk about some of the work that we've done on developing real-time adaptive models using linear regression. So in this study, we had 7 participants without disabilities doing a 2-dimensional trajectory tracking task. They were asked to track that red reference trajectory with a blue cursor on the screen. The input that the participants were providing was a 64-channel EMG sensors that were placed on their forearm. The model, like I said, is a linear mapping from the EMG activity to the cursor position Y. And in order to optimize the model parameters, we minimize the cost function f with respect to the model parameters every 20 seconds. And in order to ensure that our participants weren't having to learn a completely new model parameters every single update, we actually had them do a smooth transition where we updated the new model parameters as a linear combination of the old model parameters as well as the optimal model parameters that we found in the previous step. So here's an example of what this task looks like. So at the very beginning, the model parameters are completely randomized. So this participant cannot control the blue cursor at all. They're trying to track this red reference, but it's very, very challenging. And then actually, we're going to skip ahead a couple of minutes, maybe like 3 or 4 minutes. And now we're able to see that our participant, the model has updated and personalized to this particular participant. And so they're able to control the cursor reasonably well. And they can track this cursor on this reference trajectory on the screen. And I'll show you a little bit more results in graphical form. You can see that in the first 30 seconds of this experiment, our participant has no control over the cursor because the model parameters have not personalized. But by the last 30 seconds of this 5-minute trial, our participant has really good control over the cursor, and they're able to track this reference trajectory really well. And another really interesting finding that we found is that I told you that we had a smooth update between models, and we could either update the model parameters quickly or slowly. And what we found is that when we updated the model parameters slowly, participants and the model were able to kind of co-adapt and improve performance with time in kind of a smooth learning fashion, which is good. However, when we updated the model parameters quickly, we found that our participants and the model were unable to kind of converge to a good error, and they were not able to improve performance very much. And we are hypothesizing that it might be because the model parameters were changing a little bit too much, and so our participants might have found it very hard to learn a moving target. Next, I'll talk about some of the very, very preliminary work we have on developing individualized gesture interfaces for people with upper body disabilities. And so the reason why we're interested in this topic is because as new technologies such as augmented and virtual reality are coming out, gesture-based interfaces like the point and pinch interface that I'm showing you here are going to become more and more ubiquitous in our daily lives. However, for somebody with an upper body disability like stroke, Parkinson's, or other disabilities, it might be really challenging for them to do this kind of movement. And so we wanted to enable personalized gesture-based interfaces. And so we had a couple of inclusion criteria. One, they had to have a disability that affected their ability to interact with technology. And 2, they had to be able to move their head from left to right. And so what this means is we had a really broad range of participants, from those who had some numbness in their hands to participants who had full paralysis from their chest down. And so because of that, we placed these sensors on the person's whole upper body in a distributed fashion instead of in one location. And we asked them to do different interactions that represented common interactions with technology, such as zoom in, select, and rotate. And we only asked them to do 10 samples per gesture. And so here are some of the gestures that our participants came up with. This participant had overall muscle weakness, and so they're doing kind of a full body shoulder neck gesture to do the zoom out gesture. This participant has weakness in their fingers. They can't really move their fingers, but they have really strong biceps and triceps, and so they're doing this move gesture primarily using their upper arm. This participant has muscle weakness in their bicep triceps, but has really good forearm and finger dexterity, and so they're placing their hand on the table and doing a rotate gesture on the table. And lastly, this participant has overall muscle weakness, and so they are using just one finger to do a select gesture. And so the big takeaway from watching all these videos is that there is no such thing as a single disability or one way that our participants are doing these motions. And it's really important to ensure that these sensors are distributed across the whole body. Next, I'll tell you a little bit about how we analyze the data. So this is what raw EMG signals look like. It's very random. And so we can filter our EMG signal and perform a moving average in order to get a much smoother trajectory. And that's what we're going to put into our k-nearest neighbors algorithm. And what we found is that we were actually able to get 80% accuracy for the 13 participants that we've had so far. And that's really remarkable because we had 10 different interactions that we were asking them to do, so the baseline accuracy is 10%, and we only had 5 samples that we used for training and 5 samples for testing. We're super excited about this, but we're still collecting more data, so I'll keep you updated. Diving a little bit deeper into individual participants, so this particular participant actually had a 94% accuracy, which is awesome. And it seems like what might have contributed to that is that this participant told us that they tried really hard to make the gestures as different as possible. This particular participant, however, had a much lower accuracy of 56%. It didn't seem like they were trying to make the gestures differently. And what's really interesting is we had 2 interactions, a move interaction and a pan interaction, that some of our participants felt like should just be the same gesture. So pooling that data set might help us with improving that accuracy of gesture classification. So in conclusion, my vision is to optimize the next generation human-machine interfaces towards a more inclusive and equitable society. And optimization doesn't just mean optimizing for performance. I also want to optimize for the user's preferences, their abilities, and how those preferences and abilities fluctuate and change throughout the day. And we tend to see this trend where we take technologies, we develop them for the quote-unquote average user, and then after the technology comes out, we then try to make things more accessible for people with disabilities, or we try to use them for health tracking. And I would love to see a paradigm shift where we take into account how different users interact differently with all these different technologies while the technologies, algorithms, these sensors are being developed. That's all I have for you today. If you are interested in hearing more, you can feel free to email me. I am looking for PhD students to join my lab. So yeah, feel free to email me or come talk to me during after this at the reception. Thank you so much.